Okay, so there is a formula for what we are going to do in this video, but I'm very bad at remembering formulas. So the method I'm going to use to solve it is actually the same as the formula, but like a little different. You would know like after watching the video. Okay. So what we are to do is we have been given the group Z20 addition modulo 20 on the set of integers, and we have to find the number of subgroups. Okay, so subgroups of this subgroups of this group. Now what do we know about Z20? First thing we know is that the order of Z20 is 20, right? And then we also know that Z20 is cyclic. Okay, now let's start breaking it apart. The information. See, this order is 20. That means possible order, possible orders of subgroups can be what? Can be divisors of 20. So it can be 1, which will be the trivial subgroup containing the identity element. Then we have 2, then 4, then 5, then 10. And if we have not set proper subgroups, then obviously Z20 is a subgroup of itself. So that also, okay. So this could be the possible orders of subgroups. Now, this possible is very important here because whatever the subgroups we will get will be of either of these orders, but it is not necessary that we definitely get a subgroup of one of these orders. Okay, so I hope you know this. Like, subgroups will be of the order of k, where k divides the order of the group itself. But it is not necessary that we will definitely find the order of that, the subgroup of that order, right? Okay, in this case, we will find the subgroup of all these orders. Okay, anyway, let's begin. First thing I can see, first let's get this thing out of the picture. This subgroup will be of the identity element, which is 0. And this is, well, the given group itself, right? Now, coming to this, what immediately catches my mind is this 2. So any subgroup, let's call this H1, okay? So any subgroup will definitely have the identity element, no doubt about it, right? So it has one more element and nothing else. This implies that that one more element has to be self-invertible, right? It has to be self-invertible. And we know that Z20 contains, like, the set contains n where, okay, not like this, n belongs to this 19, that's 19, or I'll write it like this 20, right? So it is 0 to 19. So only 10 is the element which is self-invertible in this. Okay, so no other element will be self-invertible because 10 plus 10 is 20, and 20 mod 20, because 10 square is 10 plus 10, because the operation here is addition, which is 20, and 20 mod 20 is 0, right? I guess it's clear. Yeah, I was not supposed to explain this. It's pretty simple, right? So now coming to these. Now the way I look at it is, okay, we know that Z20 is cyclic, right? So what are the generators of Z20 then? C. Yeah, now begins the main story of my method, my approach, not method. It's just a different approach to the already given method. Okay. Now order of Z20 is 20, right? And suppose A belongs to, I'll call this group G. Suppose A belongs to G, then A to the power K would be the generator of this group. When will this happen? When when the GCD of K and 20 is 1. That means when K is co-prime to 20. What this means is that, let's take A as 1. Okay? 1. So what are the like powers of 1? Powers as in, 1 square will be 2, 1 cube will be 3, because it is 1 plus 1 plus 1. Remember? This group is, the operation on this group is addition. Okay? So 2 is not co-prime to 20, 3 is, 4 is not, 5 is not, 6 is not, 7 is, then 9 is, then 11, 13, 15, 16, 17, and then 19, right? Yeah, obviously not this one. So what do we get? Yeah, we get 1, 3, 7, 9, 11, 13, 17, and 19. Okay. And because these all are co-prime to this, it means, okay, it will be a lengthy video, but I need to explain this. See, 1, 1 to the power 20 is the identity element, 0, right? This will be 20, and 20 mod 20 is 0. Okay. Now see, all the factors of divisors of, yeah, factors of 20. See, if 2 I can put it as this, 4 I can put it as this. So order of, what this implies is, order of 2, this element is basically 2, is 10. This element is 4, order of 4 is 5, right? Then 1 to the power 5 to the power 4, order of 5 is 4. Okay, are you getting this? I hope you are. Okay. Now, so they will not, their order for an element to generate a group, its order should be equal to the order of the group. And when will that happen? Well, that can happen only when here, like when 1 to the power, when we have something that is not a factor of 20. So for that we need to write 20 here. It is not a factor of 20. Okay, like 3 for example. So what we'll do is 1 to the power 20 to the power 3, so that we can write e to the power 3, which is e. Okay, I was supposed to make another video on this, but okay, if anyone watches this and feels the need for me to explain this, then just let me know in the comments. Coming back to this, what we make out of this is that for a generator to generate the entire group, its order its order should be co-prime to the order of the group. Only then will it generate the entire group. And what we have done is we have separated these elements in this in the example we are taking. So this these are the generators, right? So what this implies for us is that cyclic group of all of these will generate the entire group. That means order of all these elements or the subgroup generated by them. No, they generate the entire group. Okay, so there is no proper subgroup generated by them. Now let's look at the elements which we have missed. Okay, so the elements which we have missed are 2, 4, 5, 6. Okay, that was to come there. 4, 5, 6, 8, 10, 12, 14, 15, 16, and 18 and 20. Right? These are the elements which we have missed. Okay. Now, look. Now we will. What is 2? 2 is 1 square. Right? What's the order of 1? 1 to the power 20 is e. And 1 square is 2. So what I'll do is I'll write it like this, which implies 2 raised to our 10 is e, which means that order of 2 is 10, which means the subgroup generated by 2 will have an order equal to 10. Okay, and let's just calculate it, right? It will be 2, 4, 6, 8, 10. Am I doing right? Yeah, 10, 12, 14, 16, 18, and 0. Yep, this is the subgroup of order 10. Subgroup of order 10, and the generator is 2. But this is not the only generator. Okay, now another important concept coming up. What is the order of this group? Sorry, what is the order of 2? It's 10. So for an element 2 raised to the power p, where p divides 10, which is this order of the element 2. In this case, that means for 2 square and 2 to the power 5. No. Not divides. Okay, slight mistake. When p is a factor of 10, actually. That's the same thing. Okay, look. How do I? Okay, I'll go to the generalized form later. Okay, just remember 2 square. What will that be? 4. Now look, order of 2 is 10. And we know that 2 square is 4. So if we do this, that means 4 to the power 5 is e. This implies that order of this, what would that be? Let's see. Cyclic group of 4. It will have 4, then 8, then 12, then 16, 4, 5, so 20, which is 0. Yeah, this. Okay. Yeah, I figured out what I was trying to say. Okay, anyway, so this is clear. Now, so this is the subgroup of order 5 and the generator is 4. Okay, yeah. And what I was trying to say earlier is this important thing. All the exponents of 2 which are co-prime to 10, remember, co-prime to 10, that is 3, 7, 9. I think these are the only ones which are co-prime to 10, right? Out of from 1 to 10. 1, 2, 4, 5, 6, 8. Yeah, these all, they will generate this entire group. Okay, you can try this. Why? Because the same reason which I explained earlier. Okay, 2 raised to power 10. I cannot separate 3, 7, or 9 from this. So when I'll have to put 3 here, I'll have to take the 10 as it is, using this thing. Okay, I'll use this and then go to this. And from there, I'll figure out that 2 raised to the power 3 has an order 10. Okay, if still confused, watch it again or just ask me. Okay, so now we are left with 2 square. We already, yeah, we took that into consideration. Now 2 to the power 4. Okay, what about this? Now again, we know that 2 to the power 10 is e. What is the LCM of 4 and 10? LCM of 4 and 10 is 20, right? And 4 into 5 is 20. So 2 raised to the power 4 raised to the power 5 will be 20. Will be E. Sorry. Yeah. This will be the order of 2 raised to the power 4. Yeah, this LCM thing I find easier than the GCD, which is used. I can't even remember it. N by GCD of K and N, something like that. GCD of K N A K, something like that. I don't even know if this relates to this. I can never memorize this. Okay, so yeah, whatever. Don't confuse. I'm confusing myself in the video. Okay. Anyway, so this is the method. Okay. So what will this be? Now see, 2 raised to the power 4 is actually 4 raised to the power 2 raised to the power 5. Okay. And we already saw the cyclic group of order 4 is this subgroup. Okay. Now let's see what this is. It should be same. Let's begin from here. This is 2 to the power 4 is 8, right? Addition. 8, then 16, then 24, which is 4, then 32, which is 12, then 40, which is 0. Yeah. This is the same as this, right? Yeah, this is another observation. 2 squared, 2, 4, 2, 6, and 2 to the power 8. This is 4, and this is 8, this is 12, and this is 16. These are the generators of the subgroup of order 5. Shall I write it? Generators of subgroup of order 5. Okay. Now we have covered the subgroups of order 5, order 2, order 10. Okay, what is left? Yeah, see, 5 and 15. These two elements are left from the group. Now, what about this? What is the order of 5? Order of 5 is 4, and order of 15 is also 4. Okay, so what will be the cyclic group generated by 5? It will be 5, 10, 15, and 20, which is 0. 20 mod 20 is 0. And similarly, in this case, 15 times, like 15 square will be 30 in this case, and 30 mod 20, 15 square will be 15 plus 15, which is 30, and 30 mod 20 is 10. 15 cube is 45, and 45 mod 20 is 5, and 15 to the power 4 will be 60, and 60 mod 20 is 0. So these are the these are the subgroups of order 4, and their generators are 5 and 15, right? Yeah, I hope this is clear. Okay, well, if you have any doubts, then do ask me. Don't stay confused. That's it.